Hello everyone, this is Mandeep Singh 𝐶 and today I'm back with another video discussion in which we will be talking about how we can avoid double payments in distributed payment system. This is based on one of the Airbnb blogs, and I have personally worked with payment systems for quite some time at my previous company. So I will be able to share a lot of insights here how you can design the system so that you can ensure that whenever the payments are made, the money is deducted only once. Okay, so let's say this is your user and this is your some another user. So in case of Airbnb, this is your guest and this is your host. Okay, and this is your Airbnb system in between. So in here, some money is deducted from this user. Airbnb keeps its own share and then transfer the other money to the host. Okay, so in short, like in summary, your money transfer should happen exactly once. And how you can ensure that in a distributed architecture there are multiple systems involved here, so how you can ensure that payment is only processed once with definitely lower latency in picture. If you haven't subscribed to the channel MsDeep, consider subscribing. I keep on talking about these kind of details around system architectures, how different architectures are built by large scale companies, and in general as well a lot of system design concepts. So consider subscribing, you will learn a lot of things. Continuing on the video discussion. Okay, so again, I hope you understood the concept that we have to ensure that there are no double payments which are done. The payment should be always singular. So this is what we have to ensure when we are designing the system. So we will discuss the scenarios first, like in what scenarios this can happen, and then we will talk about resolutions. Great. Okay, so let's talk about scenarios. So let's say this is your user. Okay, this is your user, or this might be your some service. Okay, and this is your payments system. Now this payment system expose some sort of APIs, and these services or these users, or like let's say this is a user app. Okay, so these user app or the internal service itself talks to this APIs of payment system to process the payment. Let's say that process this payment of 100 rupees and deduct this amount from this user, and then again other details can be taken, such as like from which bank account and all those things, like from where this amount is deducted and to where this amount has to be sent. I also discussed one similar video which discusses Uber's checkout page design, so I also suggest check out, go watch that video as well. That will also help you to understand some of the payment details and would be beneficial. But coming back to this, so one of the scenarios could be connection drop. So whenever these users are interacting with this app, right, there is a possibility that this connection is dropped. Okay, so let's say, but this request already reached to this API endpoint, but after that this request dropped from the user. So the payment system is already processing that payment request, but this connection dropped here. So there is a possibility that user is not aware of the if the payment is processed successfully or not, and he might try again. So we have to handle that scenario if the payment is already processed or not. So the connection drop is one scenario. Another thing is timeout. It is much similar to connection drop, but the timeout can also happen in, let's say, whenever these services are interacting with each other and there is some timeout configured. Okay, but in that timeout this processing didn't happen. The payment request took more time than expected, so the request timeout. So this is one of the scenario. Handling transactions involve multiple microservices. So we here mentioned that this is a service one, this let's say talks to a service two, and then that service forwards the request to payment system, and then this payment system talks to some external payment gateway, right, external PG. So then this payment is processed. So if you see, there are bunch of microservices involved here to that process that payment. Now we have to ensure that if there are multiple microservices involved, these services or like the state of that payment is in sync. Okay, we have to ensure that. So if there are multiple microservices involved, we have to ensure that the payment status is in sync. If one service says the payment is success, other services should not say this payment is failure. That throws a sync behavior in the states. Client failed to consume success failure response. So we mentioned that we have, let's say, payment service, right, pay service. This pay service is forwarding or like sending some responses via callbacks, like success failure, or via Singh calls. This service is invoking that what is the status of this payment ID. So this returns the success and failure response. There is a possibility that due to these scenarios, right, connection drops and timeout, there is a possibility that this client is not able to consume that response. So if there is a retries involved, if there are retries involved, it should be able to reconcile, or like you can say return that correct state at later point of time. So this is what we mean by this one. Okay, another thing, like very generic use case is that you click on multiple times. Click on, let's say this is pay button, or let's, in case of Airbnb, you click on book multiple times. So this is a classic problem of concurrency, where let's say if user clicked multiple times, you have to process it only once. This is any of your service, you have to only process it one, even if the button is pressed multiple times. So this handling should be present at both the places, both at user end, as in when I say user end, it means the user app. So whenever this is, let's say, user app, and this user app has this button pay. So in this user interface itself, there is some handling in place, so that even if user clicks it multiple times, it do not allow that, it only sends a single request to the backend system. Okay, but alongside there should be handling here, as well as there should be also handling as this backend system as well. This is your payment system backend, so there should be handling here as well, depending on some logic. We will discuss those logic, like what are the different resolutions, how you can do it. But the idea is, even if the duplicate request come in, the system should only process that request once. So these are the different scenarios. Now one thing which is mentioned in the document is that the state of the payment, or the status of the payment, will be eventual consistent behavior, right? When I say eventual consistent, it means that because there are multiple services involved, right, there are multiple services involved, so there is a possibility that the status of that payment is not exactly same at every time. We have to ensure that it is in sync, but it can take some time to propagate that status. So there are some techniques discussed here in context of, because in the backend, Airbnb uses the MySQL cluster. Okay, there is some master instance, and then there are replicas. So this is replica, this is replica, and this is your master sharded instance. Great. So you have to ensure that eventually all the systems, all the instances have the same status of that payment ID. There are some techniques which are discussed here. Okay, first one is read repair, another one is write repair, and last one is asynchronous repair. So quickly summarizing on what the mean is, when I say repair, basically means if the status is not correct on a particular replica, you have to correct that status. Basically, let's say this says payment status is success. So assume a life cycle of payment as this way. Okay, so payment is initiated, then payment went to processing, and from this it can go to success or failure. Okay, this is the minimal state machine of the payment life cycle. Okay, so let's say it started from initiated, then it is in processing, and then it went to success state. So right now this is the state in which the payment flowed. This is the stage 1, this is the stage 2, and this is the stage 3. Now assuming right now the status at the master instance is updated as success. Okay, but in here at replica it is only not initiated, it is still in processing. So somehow you have to ensure that this is also changed to success. This is what we mean when we say eventual consistency behavior. Okay, great. So the idea would be like how you will do it. Okay, so the some of the techniques which are discussed here is, first one is read repair. So whenever you get a read call, okay, whenever you get a read call, you will fetch the data from, let's say, all the replicas. Okay, and if the data is not same on all the replicas, then it will send that update to the replica, that update this status to the success, and it will update it. Okay, you can, this is a very famous technique which is followed in multiple databases. You can read about it. If you just Google it, you will find Cassandra references how it is used to sync all the replicas which are in their cluster. Great. Similarly, on the write repair, whenever you receive a write call, at that point of time you will update that inconsistent payment state. Okay, so this can very well happen at, let's say, if the client fired the same request repeatedly and then server takes the action accordingly. Okay, so this is the write call. When I'm talking about here, it is a read call. It can be as simple as, let's say, you are fetching that status of a payment. So whenever the status is fetched, you try to fetch the status from multiple replicas to ensure that what is the status of it, and then you can check if the status is not same on all the replicas. But just from the client per se, we will also discuss in some time that you try to fetch always from the master instance if you want the strong consistent behavior on what is the payment status. The last thing is asynchronous repair. In asynchronous repair, what we are discussing here is, when I say asynchronous repair, what we mean is that the status is synced, okay, asynchronously. You might have heard about how asynchronous system works. Asynchronous basically works on, let's say, on the event based. Okay, so that is one way that you receive some sort of event from external services and then you update the status of that system. Another thing is you continuously run some sort of table scans, okay, or some schedule. You have scheduled some cron jobs to ensure that what is the status of those payments. So this is what we mean by asynchronous repairs, that what is the status of that payment. Let's take some example, right? Let's say you have this scheduler, and this scheduler, whenever you receive a payment request, you push that request to this scheduler payment ID. Okay, so continuously you can very well assume it as a queue. Okay, let's say you are using SQS, so you very well you push that payment ID to this queue, and you continuously consume that response from this. And whenever your system consume this payment ID from this, you have a schedule, let's say, for 15 minutes. So you push that message to this SQS. You will consume the message from SQS again at 15 minutes of interval. Then you check what is the status of this payment. If it's not at a terminal status, then you try to say, or like check, how can I, like, basically check with, let's say, your external partner, what is the status of my payment. So accordingly you update that status in your system, and this very well can work on synchronizing the status across the multiple replicas. So you can use any of these mechanisms just to ensure that of all the payments which you are processing, okay, all the payments which you are processing, you have to reach a terminal state, as well as you have to maintain a consistent state among the multiple replicas. Table scans specifically, you have to figure out a great strategy, right? So this is one of the strategy where you specifically look for all the payments which are not reconciled at this moment. You don't have to check for the older payments, right? So whenever I say table scan, you don't have to do, or you only have to perform the action on the current payments which are in processing currently. This we discussed eventual consistency techniques. Now let's talk a little bit about idempotency. Whenever we want to ensure that the payment should be only processed once, how you can do it? Okay, so the one way is that if the multiple requests are coming in, okay, if the multiple requests are coming into your payment system, then you have to ensure that is already only processed once, so that the payment is not processed at 2 times or multiple times. Okay, this is what we mean by idempotency. Idempotency basically means you are filing a particular request, okay, this request 1, and if you fire that same request again, if you fire that same request on request 1 again, the effect will be same. Okay, so let's say this is the payment request, deduct amount 10. Okay, deduct amount 10, and if the payment system already deducted that amount 10, and if you send that again the same request, exactly the same request, then it will say that the amount is already deducted, and it will just send a response that, yeah, success. Okay, but in the backend it is not doing any operation. So this is what we mean by idempotency. Idempotency means, just by the definition, payment request should only be processed one, even if called multiple times, generally due to retries or unwanted user clicks. That it can happen due to retries, let's say the request timeout, okay, or unwanted user clicks. We mentioned that we have to handle that in our requirement section, or what are the scenarios in which the double payment scenarios can occur. And this is like guest is only charged once and host is paid once. We also discussed this example. Great. Now solutions on this, how can you implement the idempotency? So this is the key requirement, or you can say a key implementation technique, which is used if you see any of the payment system, right? You see a payment system or payment architecture of a bank, of a startup, or like any system, anywhere if the payment system is implemented, you will see a concept of idempotency implemented in the APIs. You ensure that if the same request is fired multiple times, it is only processed once, and the way you do it is via idempotency. There are multiple ways you can achieve idempotency. We are discussing here Orpheus. Orpheus is a general framework library. We don't have to understand how it works basically, but the idea behind is pretty simple. Okay, you create a key. Okay, you create a key. So we discussed that. Let's say this is your user app and this is your backend, and you are sending a request. Okay, now how will you identify? How will you identify if the both the requests are identical? Okay, how will you identify that? There is a value, like if you just one simple idea which you can think of is that check the parameters. Okay, check the parameters of what the request was filed earlier with. But it is also possibility that you want to process that same payment again and again. There is a possibility of that. So just to avoid that possibility, how idempotency is generally implemented is you pass some sort of key. Okay, so you generated a key here, idempotency key, which is passed alongside with one request. Okay, and this key is stored here, key one, let's say. Okay, this key one is stored here. Now if you send this same key again, if you send this same key again, this pen is not that visible, but yeah, if you pass the same key again, key one, then it will check, yeah, key one is already present, so this request is already in processing, it is already processed, so accordingly you can handle that. So this is how this Orpheus library is also implemented. You create a idempotency key and it is passed along in the framework. When I say framework, there is a possibility that the user app is directly integrated within payment system, right? But there is also a possibility that multiple microservices are interacting with each other. We discussed this in the requirements, that there is a possibility that multiple microservices are talking to each other. So in those scenarios, if a single key is passed across microservices M1, M2, M3, so the same key can be used across the systems and you can ensure that your call is idempotent. Okay, so table for idempotency information always written on sharded master. Now you are storing this key, right? We mentioned that. Oh, I removed the diagram, but if I mentioned that on a payment system you are storing that key in a database, right? But what you want to do here is that you store that key on the sharded master database. We will also discuss in some time, so that your master database do not overflow with the keys which you are storing, because the scale of Airbnb is huge, right? So you will ensure that it is not overloaded. We will discuss that in some time, but the idea here is you always store that into a master database. It is also asynchronously synced with the replicas, but you store here and then you also fetch from this master instance when you check if this key is present or not. Okay, just to ensure the strong consistency behavior. Let's say you are using some other database such as DynamoDB. In that you can say in your API call that I want a strong consistent behavior, so you can just check the consistent behavior to true, and then you can get a consistent response from the master instance of DynamoDB. Another thing is database transactions combined in different parts of code bases. So just for the simplification per se, if let's say the transactions in the code are scattered, it is hard to manage them. So just to ensure that they can be easily what you say read as well as maintained, they are combined together, and it also helps in achieving the atomicity. So let's say I want to do two operations. One is make an actional call, and then save to DB. So these are my two operations. Okay, when I say combine the transactions, what I mean is you execute this block simultaneously. Simultaneously. Or another example is, let's say in database as well, you want to save two information. One is payment record. Okay, another is history of this record. Okay, so whenever you are saving to the database, these two records either should be saved simultaneously or none of the records should be saved. So this is what we mean by atomic behavior. If there are multiple operations, okay, multiple operations which are executed, either they all are executed or none of them is executed. So all these operations are combined in a transaction block, in a single transaction block, and they are processed atomically. Okay, and again talking about DynamoDB as well, what you can do is you can specify all the transaction blocks in the single API call. Let's say uh, transact write items. Okay, and then you can specify all these blocks in a single call, so either all of them will be written or none of them will be written to ensure this. Another thing is which is very important, and it is not much specific to payment architecture as well, but any system which you are developing, any system you are developing, you should ensure that your errors are classified properly. Whenever you are exposing your APIs to outside, it could be very well possible that your client is internal. It could be possible that you are exposing these APIs to external clients which are not in your organization or not in your company, but the classification should be done properly, which specifies if the error is retrievable or not, if the API call is retrievable or not. If you are, let's say you are sending a 5xx, okay, if you are sending a 5xx, you ensure that it is a very simple implementation, right? You just, let's say this is a is retrievable block, you just send it either true or you send it false. Okay, so this way clients will know if I have to retry this request or not. In case of failures, client will know if there is a benefit to retry this request or not. Another important thing here, how the request is processed in the system. Okay, so this request is divided into 3 steps. The request is divided into 3 steps. First is pre-RPC, then RPC, then post-RPC. RPC is remote procedural call. So remote procedural call means it is a system and we are executing this call somewhere else. So let's say this is your payment gateway Razorpay. Great. And it has exposed some of the APIs. Okay, and I'm executing this API here. So this is basically your RPC. Great. I'm not sure if I have already created a video, but I will see. It should be there, but the idea is pretty simple. Okay, idea is pretty simple, and you can also read this about RPC in my upcoming book, which is System Design on AWS. If you follow me on LinkedIn or anywhere else, you will see that I was working. It is already completed. It should be available in some time for physical purchase, as well as it will be available on O'Reilly platform for read. You will read. You will understand a lot of these concepts, and we have also discussed payment architecture in that book. So yeah, coming back to our discussion, we have 3 steps when you execute a payment request. First is pre-RPC, then RPC, and post-RPC. RPC basically means you are sending the call to outside. Okay, sending the call to outside for the payment execution. So in case of payment system, in case of pre-RPC, what you do is you just save the request. Okay, so let's say this is my idempotency key and this is my payment ID. So this information is saved to DB. So this is my step 1. Second step is you actually call a payment gateway to execute that request. Okay, you actually call that payment gateway to execute the request. So this is your RPC. And third step is update the DB. Okay, so either the response is received in the same call, which is the RPC which you made, or you receive a asynchronous response via callbacks or some other mechanisms like that, right? So this ensures that your logic of external interaction is limited to this, and you, before calling to the external vendor such as Razorpay, you have that information in place that yeah, this is the payment ID which I have created already. Okay, and this helps in scenarios where whenever you are making external calls, you have to have that context in your system, that what is the call which I have sent externally. Okay, this way if this call times out, you will have some reference in your system that you can again later on check with Razorpay that yeah, this is the payment ID which I created earlier. Were you able to process it? If you able to process it, what is the status of this payment? So you are ensuring the payment is not processed multiple times. Understanding it via diagram, which I took it from the blog itself, Airbnb blog. So this is your pre-RPC, first database comment. You just find idempotency P and determine if retry is possible or not. If okay, so basically you are saving it to a database. Great. So this is what you are doing in the pre-RPC step. In RPC, you are talking to external vendor. In post-RPC, you are updating that database, and this is the transactional block which we are talking about. We are combining multiple transaction blocks, right? So This is the first one, pre-RPC step. This is the RPC step. We're actually executing the payment, and then post payment, or like post RPC, you are received the payment. So just update the response of that payment received. Great. So this is the general idea. You are ensuring that you are keeping idempotency key which flows through the system, which flows through the microservices, whichever multiple services which you have, and then finally you are breaking the payment request into multiple components, or like multiple steps, which is pre-RPC, RPC, and then post RPC. Great. So this is the overall idea about how the implementation works. But to ensure that the system works without any interruptions, there is also some responsibility which has to be taken by the client. Client is invoking the payment service, so there are some responsibilities which client should also take. Unique idempotency key for each request, same for it. Okay, so if there are retries, you should push the same, you should use the same request. Okay, if not retries, you should create a unique idempotency key just to ensure that your payment is successfully processed. In the payment system, we are anyway storing the idempotency key if it is stored, it was processed earlier or not. If it was processed, then you will not process it. So the client has the responsibility to send a unique key always. This key is persisted to database for later use. Get just to like, this will help to identify, yeah, if it was already processed or not. One thing which we want to discuss here is that once the idempotency key is used, okay, idempotency key is used, and then it is also stored to a database. Now one, and the payment has reached to a terminal state, let's say failure or success, whatever terminal states we are maintaining of a payment, the payment has reached to a terminal state. Okay, and once the terminal state is reached, do we want a mechanism to reuse these idempotency keys? Okay, you can take this decision at the time of your system, like whenever you are architecting your system. Do we want to reuse these idempotency keys? If you want to reuse those idempotency keys, you will have to have some sort of mechanism so that you clean up the older idempotency keys. Great. And if you can somehow ensure that you will always create a unique idempotency keys, in that case you can just say that I will just keep on maintaining the keys, and the system should ensure that this idempotency key is unique at every request level. Okay, and another thing is you can also associate some time frame. So if you have used DynamoDB, there is concept of versioning and also a token which you can send. I think the token is related to idempotency token only, but I am forgetting the name. But the idea behind that is there is an interval of 10 minutes. Okay, if in the 10 minutes, if that same request is sent again, the idempotency behavior will hold. Okay, so if the same request is sent again, it will be rejected if it is already processed. Okay, so that mechanism is also possible, and it depends very well on how you are architecting your system. Another thing, mutation of request payload is not done between the retry attempts. Okay, so how our system works is, this payment system, we have removed all the diagrams, but how our system works is that our system operates on the idempotency key. Okay, our system operates on the idempotency key. Our system, what our system operate on? Idempotency key. Now whenever I receive a request, I will check in my database if this key is present or not. But the client has a responsibility. If the same request is sent multiple times, the other parameters in the request are exactly same, because I am only checking on that key. If other parameters are changed but the key is same, I will not be able to identify that. Okay, so this is what you have to ensure. And just in the context of payment, how you should do is, how you should perform the operation is, let's say once the pre-RPC step, in the pre-RPC step you should record all the information. Okay, let's say what is the amount, from where the money is deducted, so money to and money from where money is deducted and from where the money is sent. Okay, so this you will record at the time of pre-RPC. Now whenever your RPC executed, or let's say some retry came in, you will use the information from this, which is saved to the database, instead of relying on the parameters which are sent in the retry request. Okay, so this way you can ensure that, let's say at the first time the amount was sent 20 and later point the amount is sent 20, you will only use the 10. This way you are ensuring that you are not depending on the client to send the unaltered response, or like let's say the app is hacked in between, and instead of it was earlier started with 10 and later it was converted to 1000. So the payment system should work as expected. Okay, proper retry strategies with exponential backoff and jitter. We have already discussed this in a independent video as well. How jitter helps, how exponential backoff helps, and what is the proper retry strategy along. We should consider using token bucket algorithm for a proper retry strategy. Okay, so there is separate video for that. Go check that out. It will be really helpful to understand, and that is a very general video which talks about in general in the your system architecture, whatever you are developing, how you can use the retry strategy and how you can implement it. Some additional considerations overall on the system. Each API request has a expiring lease. Okay, each request acquires a database level lock on idempotency key. The request can be retried by the expiration lease. So what we mean here is that whatever information you are saving to this database, uh, let's see this color of pen. Yeah, this is visible. So whatever information you are saving to the database, there is a lock on a particular key for a particular time. Let's say 5 seconds. 5 seconds is too less. Since we are talking to the external vendors, let's say 30 seconds. Okay, so for this particular time of request, you are allowing that request to process. Okay, you just disregard, let's say, retries on that request or something of that sort, so that it is not doubly written, it is not concurrently accessed by multiple requests altogether. Okay, so you're ensuring that via holding a lock against that request. Recording the response. How will you record the response? So the response of the request is stored in database for transaction which reached the end state. This is great, as the response is stored can be quickly returned to the. So this like what we mean here is whatever information we are processing, or like whatever payments we are processing. So this is your payment system and this is your payment DB. Okay, this is your payment system, and this payment system is talking to some external partner. Okay, external partner. Now this external partner, whatever response you are receiving from it, you are also recording to a database so that you can use it to serve the client request. These clients are talking to this payment system. So let's say whenever you receive a request from client that what is the status of this payment ID, you are not going to the external vendor again and again. You can just check in your database what is the status. Okay, so you can quickly return those response. One thing, read idempotency information from the master DB. This we already discussed, that we want to ensure we want that it is already always read from the DB instance, but we also mentioned that one problem which might occur. Okay, there is a limited size, so it is very well related to how much vertically you can scale it vertically. Okay, at some point you will have to move to a horizontal scaling nature. So just for that, the database, or like from where the information is fetched, it is sharded depending on the idempotency information, which is of high cardinality. Okay, and it has even distribution, so you can ensure that the database or the sharded instances has even load basically. Okay, so it is sharded by the idempotency key, and then there is even distribution, so that you do not face what we call hotkey problems on this database. Not a single instance is accessed all the times, causing problems on a single instance. So this is all we want to discuss today. I hope you understood how you can avoid double payments in the distributed system. If you haven't subscribed to MsDeep Singh channel till now, consider subscribing. You will learn a lot of things, I guarantee that. But we will meet again with much similar discussions and other details, lot of architectural discussions about large scale systems. Till then, stay safe. Tata, bye bye.